So today we're going to be looking at a presentation on the optimizations for digital forensics application development under Linux with Mathematica, obviously. But before I get into the presentation itself, and rather than just read off the slides, what I really wanted to do today is I wanted to give you guys an actual demo of some of the work that I've been doing using Mathematica. So I'm going to show you a picture in a minute, and I'm going to show you with software developed using almost entirely or exclusively with Mathematica. You're going to see why we can identify that this particular image has been heavily modified. So that's part of what would fall under the category of image forensics and image enhancement. So I'm sharing my screen. You should all be able to see the basics. So this image, because it's a public domain type image, I got it from this web URL. So I'm putting it out there. The image was taken by some photographer that I cannot remember offhand what his name is, but you will find his name if you go to this link here. The image was taken with this particular camera, interestingly enough. Now, to find the particular issues with this particular image, here are the list of at least 20 items that I found a little bit earlier, just after lunch. There's a whole bunch of other issues that would give it away if you know what you're looking for. And that's what the software is going to help us to do today. But just so we have the list right here, so you can see it. Oh, hold on. 18. Oh, I forgot to add a couple points, but keep these in the back of your mind. And bit by bit, what I'm going to do is I'm going to bring in these screens from my other monitor, and we can begin to look at it. So let's look here. The image data. What do we have in terms of this particular? Oh, hold on. Where is the actual image? Give me a second. Where is the image? Da, 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 da. Bear with me. It's coming. Close enough. We'll use the thumbnail. This will be good enough for today. So that's just a thumbnail. It's always, at first, you should always start. It's always a good idea to see if the image actually has a thumbnail integrated in it, especially for JPEG type images, PNG, TIFF, and other types of images. Almost always will have a thumbnail. And the thumbnail number one should always be in the correct position. So that is to say, as it is here. The image itself should be or I should say the thumbnail should be a representation of the correct orientation of the actual image itself. So this is what the image looks like, more or less. And I'm going to move this out of the way. That being said, let's see if the actual metadata of that image carries what's there for the camera model. And they're going to say to you pretty well, and the answer is no. Very little information is of use here. If we go to what will be extracted using an XF tool, it's an open source file metadata extraction tool. We do see it's a JPEG. We do see it follows basic type DCT or discrete cosine transform Huffman coding. The type of subsampling. And that's about it. Not a whole lot. Quality is set at 60%. That's what you would typically consider acceptable for web type use. Not incredibly useful. Okay. Let's go over here to another plugin. So these are all plugins that I developed for my framework. And interestingly enough, if you keep your eye on here on these particular points right there, one of the very first things we're going to start seeing is in the Rgb Color Space. There's a whole bunch of color spaces that are supported here. The one of most interest to us here, I believe it's RGB. So we're going to go back to RGB. If we set the correct contrast, brightness, and gamma here. Oh, hold on. This is more or less what the picture should be looking like. However, set this all the way. You can begin to see the red looks a little too red, doesn't it? It's looking a little too bright, and the hair seems to be doing a little too nicely, given the change in brightness and contrast. There has definitely been some modifications made to this image. Let's keep going. Let's bring the gamma all the way down. And what sticks out? The hat, so her hat has absolutely been changed. There is way too much red given the amount of gamma that's put in this image, or that we can actually see here. The bangles that she has are been changed and modified as well. You can see there's been some changes here. Yeah, I know maybe yellow might not be obvious to see. I'm sorry about that. Maybe I should have done an inversion on that. But you can definitely see there's changes. So these are some of these are blemishes. Some of these are direct modifications to the colors. So we'll bring that down here. Let us go to the color space. What can a color space tell us about this particular image? We can see, obviously, there is a great deal of red. That goes without saying, it doesn't it? But there's also a lot of blue. I don't see a great deal of blue in this particular image. That's very interesting. Green, yeah, okay, I could get green to an extent because it takes blue and yellow to kind of make yellow. It takes blue and green to make yellow, excuse me. But there's a lot of blue. That's kind of suspect. Hold on, I have many plugins. So this framework that I developed about a little bit more than a year ago, has about 80 plugins, and I've activated about 17 or 18 of those plugins, just so we can get an idea, because it does sometimes take quite a while to actually generate the image or to generate all the output. So here we're not seeing a great deal. You're not seeing an incredible amount. However, what does stand out here, hold on, bear with me. So what does kind of stand out is, what color space was it in? This looks like it's been artificially added to her eyes right there. That looks like it's been artificially added. Let's see what else we got. This looks a little too bright. Let's keep going. Yeah, it's not really working for me there in that particular sense. It does look, if you look at the two straps here, this one looks much too bright. The hair, I know there's some contrast and shadowing, that always goes without saying. Nonetheless, yeah, this is the one. This is the one I wanted to show you. Well, at least one of them. So here you can definitely see what's been modified, at least to some extent. There has been some retouching here, touch up. There's been some touch up here. And this is not just about shadows. Somebody, you probably use the photographer in question, most likely used Photoshop, made some changes, made some modifications to the colors, did some smoothing. Also did what looks like either blemish removal here or possibly some thinifying. I'll go back to that list there that I had up just earlier. So I'll move this back down because time's running out. We don't have all day to go through it. This is not a particularly helpful. This is more of a statistical type point of view. If you're doing a very statistical type of analysis on an image, not especially helpful for us. The only thing that this is going to tell us here is that the only thing that this particular thing here is going to tell us is that there is a little too much green, even though it didn't actually show up in the other in the color breakdown that I showed earlier. But that's not particularly helpful for this type of image. File hashes, not especially helpful here. This one is what I wanted to show you. This is the one. So in the Lch color space, this is where you begin to truly see what has really been retouched. So this has been touched, this has been retouched, the hair has been touched. This we don't see necessarily the red being reddened. However, you'll see later on the red actually has been changed. The eyes have been enhanced, probably eyelashes, maybe removing the sclera, the whiteness of the eyes. This looks like the background is so uniform that chances are this image was actually copied and pasted by doing the proper type of cutting. I won't myself try to do that because I'm not particularly an expert at that. I've never had a really steady hand for that kind of work. You can absolutely see that this image has been retouched here. Interestingly enough, her hair is largely okay, largely, but you can really see this shouldn't be there. Neither should this. It doesn't show everything. You need to use a variety of different plugins to try to identify various issues with a particular image. Almost never will you have one particular image that will just, or one particular plugin that'll show you so many points that you can say, wow, okay, there it is. Rarely is that the case. Rarely. Since this is a JPEG image, the thing of the most interest here is not going to be this plugin. It's going to be, hold on, not that one, not that one. Yeah, JPEG. And because I have to speed this along, entropy filter analysis. So these are going to be the two things that are going to be the most interest to us. Yeah. So entropy analysis or entropy filter analysis, what's interesting is with JPEG images, each time you save and resave a JPEG, the quality of that image continues to degrade. Now, what's interesting here is this is normal type degradation. This is not. This has definitely been changed. This has been touched. This has been touched. This has been touched. This is extraordinarily bright and extraordinarily uniform. It shouldn't be like that. So definitely. And yeah, here too, you can also begin to see a little bit. You can just need to look at the brightness. What is so bright versus everything else? The face, it's a little too uniform versus everything else. And this is a little too bright here, as are these, the bangles, as is this, as is this. Here you can see this image was definitely copied and pasted out from another image. So the photographer did a cropping of it, copied it, and look at the background. Much too uniform. So it gives you a little bit of an idea, kind of what I've been working on a little bit over the years. This is one particular framework. If there is time, I'll try to show you some other things. If there is not, well, maybe perhaps another time. So we're going to jump straight into the presentation. And here we go. So the who, the what, I am. I work for the Department of Defense for the Government of Canada. I work as a digital cyber forensics analyst and researcher. Quickly, my IT background is I worked in mini computer mainframe type environments back in the late 90s and early thousands. Up until 2001, where I joined in with Defense R&D Canada, and I joined up there to start working in their Unix park for support. And bit by bit, I managed to move up and move on into other and exciting things. These last years, I've been working extensively in Mathematica and with Mathematica. You can go through the entire presentation yourselves later. Everything is completely extendable. You can go through it all as you see fit. There's a lot of stuff in here. This is easily an hour-long presentation, maybe more. What I can talk about quickly, these are some of the frameworks and applications that I actually have finished developing. They're fully functional. This is a very interesting one. So this was for a for vehicle network data validation, specifically forensic data validation. I will show you some small components of that. There's some pieces of code from that particular program in here as well. There's a bunch of others that I've been working on too, on and off over the years. My particular background is largely in the lower level languages, so third generation languages like C, a little bit of C++, not too much. OpenMP, MPI, touch of PVM, lots of COBOL. I did lots of COBOL years and years ago in a completely different life. So why optimize? The takeaway, so I also put in the takeaways here so it can speed things along for everyone. The main takeaway, why do we want to optimize our software? Largely because software costs, computers cost, resources cost. You definitely want to try and get as much as you can, squeeze as much as you can out of everything that you have. Everything costs money, and at the end of the day, you want to get the bang for your buck. That being said, there is so much you can choose in terms of being able to try to maximize performance. Most of us don't have the ability to run on supercomputers. Most of us don't have the ability to have large, giant clusters of computers lying around in our basements. So most of us work on PCs, workstations, those kinds of things. Myself here, my lab environment in my office, it's largely a couple of, it's three workstations. I have 3 workstations down here. The main thing you want to consider, from my point of view, when you want to begin the process of optimizing, is always consider the flow of your data. What type of data are you looking at? What type of data are you working with? How do you see and envision that data being processed? Where is it coming from? Is it coming off the network? Is it coming from disks? Is it coming from some kind of other I/O? Do you have enough memory? Do you need more memory? The CPU type CPUs you will plan on using. Do they adequately support parallelization, adequately support multi-threading? Do you require specific types of programming options? Do you need programmers? Can you do it yourself? There's a whole bunch of things to really consider. But the main takeaway here is memory and CPU. Those are the most important things. And I'm going to place a great deal of emphasis on SMP, so symmetric multiprocessing, which involves at least 2 physical CPU sockets on a motherboard. Why? Because this is where you're going to be able to get larger memory systems. Larger memory systems mean you can put a lot more in memory, have to rely far, far, far less on swap. Swap is going to be one of your great killers in performance. It will be, regardless, even if it's the fastest PCIe, NVMe, SSD, doesn't matter. Swap a swap. You'll never get to where you want to go on swap. So RAM is great, and the only way to get terabytes of RAM is to go towards SMP type systems. So when you're optimizing, the main takeaways you want to get here, optimizations are costly. It takes a lot of time. It costs money to have someone sit there and look at the code. How can I better write the code? What could I change to the code? Are there tweaks I can make to the operating system? Are there tweaks I can make to my work environment? Things I can streamline? Should we get better hardware, better software? These are important things to really take into account. And again, I really don't want to get into those little things. I'll leave you guys to go through those yourself. The main thing on CPUs is, while I would tell you I would love to put together a presentation on GPU programming, GPUs are very much low-level type programming, save for a few frameworks that are sort of functional, kind of, sort of, depending what you're doing. That largely leaves you with CPUs. So with the standard CPUs we all use, AMD, Intel, the best way you're going to be able to do scalability is going to be through multi-threading and parallelization, through and shared memory and vectorization. I cannot overstate the need for vectorized computation. Give me just a second. Yeah. An important fact to know here is that Mathematica does use the Intel MKLC libraries. So when you do certain types of operations, even uncompiled operations, your performance can be greatly enhanced if you are able to vectorize those type of operations, or if you're able to correctly state the problem through a form of parallelization, or through a form of some other operation, addition, subtraction, division, multiplication. You can greatly improve performance. There's no way I'm going to have enough time to do all this in 30 minutes. There's no way, unfortunately. Again, I'm going to leave you guys to go through the presentation itself. The main takeaways, there's a few things I do want to show you, though. The main takeaways here for CPU, for this particular point here on CPU, Linux, and Wolfram Data Language, is Linux provides a whole slew of capabilities to adequately prioritize your work, schedule, change the priorities, change the threading capabilities, change the scheduling, most of which can be done through the command line, some of which require sometimes occasionally kernel changes, kernel recompiles, reinstalls, and reboots. Typically, you don't have to do the third one. Typically, the default scheduler is more than adequate for the vast majority of types of jobs. That being said, I will invite you to go through it all yourself. The main takeaway here, though, especially for those of us who want to use large memory systems on SMP type computers, is NUMA. So non-uniform memory access is what's going to enable multiple CPUs sitting on a motherboard with memory banks spread all across, a more uniform type of access to that memory. So what essentially that means is, it means the memory that's being utilized is going to be distributed across the various banks of memory in a more uniform type approach that's done at a much lower level outside the operating system by the BIOS. Operating system support is usually available in most distributions of Linux. And interestingly enough, it's almost never actually required to be active in the operating system to get maximum performance. So those of us who want to use NUMA, and you really should use NUMA if you have a large memory system, with an SMP. So NUMA does not exist on a single socket machine. You may have NUMA-like capabilities in your BIOS, but you will not have NUMA cache NUMA cache coherency, also called CC NUMA. You will not get that, unfortunately, on a single socket machine. There's a whole bunch of commands you can use, like I already kind of hinted at. There's a bunch of things you can do to improve performance and to improve all the various aspects of scheduling and priorities. You can go so far as to directly modify CPU sets, affinities, scheduling priorities. All these can be done through proc, the virtual file system that the kernel uses. So many things you can do. I leave you guys to go through that at your leisure. Important takeaways here, though. I have some useful examples here. This I'm going to increase for myself because I'm not wearing my glasses. Oh, hold on, I put that 150. Yeah. The idea here was I wanted to validate, one, is hyperthreading worthwhile? Sometimes it is. Is it worth using operations that use lots and lots of threads, far more than would normally be supported? So I'll give you the example. My workstation I'm using right here, right now, has 48 logical cores with hyperthreading, without 24 physical cores, with 2 physical sockets. Interestingly enough, if you use far too many, and this is how you would set the number of threads, if you use too many threads, you actually can get slower performance. With lots of threads, but less than that. So set that to 72. The timings are a little bit better, but not a great deal better. However, if you do use for these kind of operations that I'm going to show you here, so these are vectorized operations. These are a vectorized type of operation. This is not. This is not. So regardless, if you throw hyperthreading 48 cores, this is not going to change a great deal. And without hyperthreading, just setting to 24 threads, not exceptional performance. The best performance is with hyperthreading. For multiplication, you have to benchmark the types of operations you want to do and validate for yourself. Is it worthwhile enabling or disabling certain types of hardware features or software features, because hyperthreading requires operating system support as well. An interesting point here was a square root. Square root, as some of you may know, can be very slow, not by itself, square root can be very slow. It can be a complicated type of operation to carry out. So these are my timings with I set to 7, so up to 100 million, I believe. However, if you vectorize it, and interestingly enough, this type of operation can absolutely be vectorized, interestingly enough, and the results are exactly the same. These results are exactly the same results as these, exactly the same results, minus these 2 because I added an extra 2 here. And look at the massive performance gain. And this also applies to cube root, it also applies to surd, and it also applies to a few others. Interestingly enough, that's not documented. It's worthwhile using those kinds of operations when you can. Myself, in my own kind of work, the types of operations I use the most are largely these types. So I do a lot of data partitioning and data reshaping, lots of tallying, lots of sorting, differencing, especially if I want to do certain kinds of enhancements. Sometimes it's nice to subtract one set of numbers from the other. Summing the numbers as well. I do a lot of spectrograms in my work, matrix plots too, list plots. The main takeaway, I'll let you guys go through all those points yourselves, but the main takeaway for list plot, if you're going to do a list plot, floating point is faster. If you're going to do matrix and relief plot, integer is much faster. Same thing again for the spectrogram. Summation, floating point is much faster. Differencing, I was surprised. Differencing is actually faster if you use floating point, interestingly enough. So I'll give you an idea of the kinds of experimentations I ran. So set this, here we go, make it as minimally floating point as possible, do the difference, run it 30 times, and here are the timings. Gives you an idea. You do get a performance enhancement. There is. Sorting, integer is faster. Tallying, oh, the largest surprise was the tallying. So integer tallying is magnitudes faster than floating point. Magnitudes faster. Same set of numbers. What an incredible difference. I was really surprised on that one. And reshaping as well. Partitioning is good. Array reshape, if you know the size you're really looking to get, you're going to get better performance. We have a few other enhancements to be seen on slide 27. So the main takeaway, SMP and SMT. So Linux fully supports hyperthreading, symmetric multi-threading, symmetric multiprocessing. It fully supports NUMA. It fully supports CC NUMA. It supports a wide variety of system schedulers for the kernel that allocate work to the CPUs. All of this is available to you. Sometimes, however, it can require a lot of work to get certain features up and running, especially if you have to do some kernel recompilation. That can be a little fussy on occasion. The CC NUMA, the main takeaway here, for if you have, like I do here, larger machines, what you want to do is you want to enable NUMA, CC NUMA in the BIOS and absolutely have it disabled in the operating system. And you absolutely want to set your processor cache settings to their most aggressive settings. This will definitely increase your performance. My overall benchmarks with and without, just for fun, that I did, I was curious. I'm going to share those here. The results are, so I explained how it's done. For my SMP machines, I get a 5 to 6% performance enhancement with NUMA, hardware on, software off. Interestingly enough, auto compilation. So what you would take by setting set system options, compile options, and then inside there's an option for, here it is. So with the table compile and with the map auto compilation on, you can get further enhancements with NUMA and CC NUMA. So altogether, I got about a 10% I got an approximately 10 to 11% improvement in overall application performance for myself for the types of applications I'm developing and using here with NUMA activated and auto compilation. Certain types of operations with auto compilation, you will see table and map can actually be faster and more efficient than the parallelized versions. Very interesting. The main takeaways here again from the listable functions. So there's a tendency to believe that listable functions are by themselves multi-threaded. Many of them are, not all of them are. Not all listable functions are especially efficient. Often there are ways to make them more efficient. Of course, when possible, use the built-in functionalities in Mathematica. That goes without saying. Do not rewrite the wheel when so much has already been provided for you. And there is a great deal already provided here in the system. There's a great deal. So I'll give the example here. Prime Q. Prime Q is very slow because determining whether a number is actually prime is actually quite difficult. Many divisions have to be done in order to get there. And we're going to see there's a much, much better way. I can get this down to about 20 seconds. Integer digits. This is a function I use a great deal. And the issue with integer digits is it as well can be very memory hungry and very slow because it's a hard problem to solve. So here are the vectorized operations. Here are the non-vectorized operations. Massive difference in performance. Massive, massive. With respect to parallelization, there are so many options to using parallelization. Like I said, I really should have gone for an hour on this. The main caveats that you always need to keep in the back of your mind when you're using parallelization is when you set up a problem and you're using, say, for example, like parallel map integer digits versus parallel table integer digits, depending how you set up the problem or how you phrase it, the performance is almost never going to be identical or nearly identical between the two. Another issue is also it typically helps to have the data pre-generated. So the example I'm using here is I'm using random integer to pre-generate the data that I want to look at. It typically is more beneficial to have the data ahead of time, feeding it to the parallelized functions than not, typically, but not always, and there are exceptions. And I provide a few of those examples here. So things to consider. I have a few things that actually do work, some actual code that I actually want to show you. So this is a little Gui selector, and it's supposed to work. So if I, okay, run that. And my files are already predefined. Okay. Oh, so normally I would say that. Click the options I'm interested in. And normally it would work, and I'm so embarrassed that this didn't work here. Oh well, we move on. Given that it's already 4:33, and given that I'm already past my time point, I'm going to run straight into the example here. So checkpointing. What's the point of checkpointing? In a nutshell, when an application provides checkpointing, it provides a form of recovery of the state just prior to it actually crashing or reaching some kind of massive error. This was something that was done a lot in the old mainframe days. COBOL applications, for example, have a lot of checkpointing built in. Myself, sometimes I'm processing very large quantities of data, and I have no interest to have to continuously go back and rerun a day, 2 days, or more of an operation. So I will typically set various points of checkpointing in my applications. And this, in theory, is already done. It's done. And all I need to do, so this is one way to do it, to set up very quickly checkpointing. And there we go. So this is the actual numeric array. This is almost a gigabyte, 1 gigabyte in size. It's a numeric type array unsigned int, and there it is, completely ready to be used. And here's another one. So this is a visualization that I had saved earlier. So this was the kind of work I want to pass it on to an analyst later on, say. I don't want to ask that person to have to go back and rerun the entire process that took, say, 10, 15 minutes. The data is already pre-generated, let them use it. So this has already been run. I will not run it again. I'm going to load it from disk. All right. Oh, and it crashed. Oh, yeah, that crashed. And I see exactly what I did. I should not have run this. Doing this, what I did is I just overwrote the file that I actually had. Well, anyways. I'm rushing too fast to try to get through it. That's the problem here. Memory management. There are so many things I could talk to you about. I could talk about memory management in Linux, having worked in large mainframe environments for years. I could talk to you for quite a long while. The main takeaway is you want as much RAM as possible. You want to minimize your use of swap. If you have to use swap, you absolutely want to go with the fastest type of swap. You absolutely want to maximize your use of RAM compression. Linux does support RAM compression. You want to minimize the fragmentation of your memory to the extent that you absolutely can. You want to reclaim as much memory. Mathematica is pretty good at reclaiming most of its memory, but on occasion it needs a little bit of help. And there are some tricks to getting that memory back. And I'm going to have to let you go through those later on. You want to clean up your parallel kernels. The parallel kernels are probably the worst of the bunch. They tend not to release too much of their memory when you've run it. And it becomes especially apparent when you're running very large operations. So if you're running gigabytes of data on a large machine, you're running it many times in a parallelized fashion, you're going to eventually wind up in a situation where there's no more memory left for the kernels. And either the application will crash or Mathematica will crash. There's a bunch of tips and tricks that I provide. Unfortunately, I'm not going to have the opportunity to go through those because I'm pretty much out of time. That being said, I'm gonna invite you guys to go through all these points, unfortunately, on your own at this particular point. There's no way I'm gonna be able to do it. But you have so much code. So I provide a whole slew of timings, results, breakdowns, points to consider. That point about the prime Q earlier, there's a better way to do it. And a better way to do it is use bool. Because prime Q returns false or true, if it's prime or if it's not prime, using bool instead, which returns 1 or 0, can so greatly increase your performance. So those timings earlier that were well over 120 seconds, my best timing to here is this one. Not bad. Not bad at all. Not bad at all. And there's so much. I wrote this presentation in 2 parts. One, to share with you guys, but also in another way to kind of document it for myself. I got tired of always running back and forth. How did I do that? How did I do that? I don't remember, because I got the attention span, unfortunately, of a squirrel all too often, and memory is not always all that much better. But putting it down like this, it's going to be a lot easier for myself too, in time to keep this kind of documentation, self-documenting stuff going for myself, and to be able to provide it with other colleagues and provide it with the community too. So again, I'll invite you guys, go through it at your leisure. When you have questions, don't be shy. If you have technical questions, technical comments, points, please, by all means, reach out, email me. This is an actual email address at work, so you can get me here. Expect a turnover of a few days for a response, but typically I will respond, typically. I'm sorry that some of my demos didn't quite work out the way I would have preferred, but I am very happy that my image processing application actually did work today. I tried working that one out last night and I didn't have mixed results, but today it worked out well and I'm really happy on that. So let's see. Oh, okay. Oh, okay. Okay. And I'll respond to the chats in a little bit. At this point, I'm going to probably stop the presentation at this point. Again, if you have questions, don't be shy. Reach out. You know where you can get me, and I'm more than happy to share any Linux insights that I have with respect to Mathematica. I'm more than happy to share any points I have on optimization that I really should have scheduled for an hour, but I'll know better for next time. So until then, cheers, and we'll see you guys another time. Bye-bye.